So our company basically came out of Amir's lab together with Warren, so we started working on treatment and helping advise me on starting this thing, and we're basically going to take a look at how we use reinforcement learning for peptidomimetic macrocycle discovery and optimization. So when we talk about the pharma industry today, it's about, depending on different publications, about $2 billion to develop a drug, where 85 cents on the dollar goes to the garbage. So we like to make jokes about the government, but we're less efficient than they are. That's not a very good situation to be in. And when we think about the problem with polymer drug discovery, and this is also true for GMS, is a huge, huge chemical space. So if we're talking about the chemical space, we're talking about the number of monomers to the power of the polymer size. If we're talking about 10 pairs of the 20 naturally encoded amino acids, we're talking about 10 to the power 13. Today, with PeptiCom, we have about 500 subunits, so we're at 10 to the power of 27, just 10 pairs. So this is a huge, huge chemical space, and it's too large for high throughput screening, that's for sure. And techniques such as phage display library basically took the first step in making peptide drug discovery possible, because they're actually using DNA encoding to produce mass screening, and they're at about 10 to the power of 13 in this case. But life is not perfect, that's why we're here. So when we're talking about the painful price for peptide discovery, it's costly and inefficient, but that's true for many drugs. 3 to 7 years to discover a drug candidate. And then when we talk about optimization challenges, especially when we're screening primarily naturally occurring amino acids, we're talking about a very, very bad bias from our own evolutionary utility function compared to what's going on when we're looking for drugs. So if I'm your body now, I'm telling you that I want your proteins to last a very short amount of times. Why? You don't want a protein running around in your blood system for 2 years. They'll get polarized, it may have acetylizations, it may have phosphorylations, it may change its function altogether. Something that's an agonist may become an antagonist. We don't want that. So, and I always like to describe it as having a chef live inside your house. If you had a chef work for you 24/7, you'd never have yesterday's leftovers in the microwave, right? You'd have a fresh meal every time. So our body can produce as many proteins as it needs. They have been evolutionarily set to have short serum half-lives, poor oral bioavailability, so they get digested quickly and destroyed. And that's not what we want in a drug. And of course, because we can't teach an all-dog matrix, although some in companies such as PeptiDream in Japan have taught DNA to encode for a few more non-natural amino acids. Let's say you can't teach an all-dog many matrix, so you can't cover the whole chemical space, you can cover a very small section of it. And at the end of the day, when you screen in the lab, you don't have a 3D structure. You didn't have to go for X-ray crystallography, which may be quick and cheap or may be extremely expensive and lead to nothing, to get a 3D structure to go from hit to lead. So when we look at a success story, we're talking about Merck's LDL, LDL reducing PCSK9 inhibitor. We're talking about a discovery process of about $4.5 million in raw pharmaceuticals. With lead optimization and clinical work at Merck, it costs another $12 million just to get the lead molecule and look at the nice number of years. But when you look at the molecule, it's beautiful. It's thioether cyclized peptide that binds PCSK9 and prevents its interaction with the LDL receptor. So it's a big market. Peptide therapeutic market is $50 billion and growing rapidly because of the advantages that we have with bigger molecules of polymers, especially the inhibition of protein-protein interactions. And what we did in PeptiCom is basically took this thing to virtual screening. Virtual screening is essentially mass docking, and today we're doing this on cloud framework, so we're using about 500,000 CPUs for docking session. But that's not enough. Why is it not enough? Why can't we just buy docking algorithms like from Schrodinger and just run them on the cloud? The reason is that we have a very large chemical space. So even with cloud computing, even with 100,000 or a million CPUs, 10 to the power of 27 is not going to be covered. Also, each individual experiment is going to be not too simple because they have many rotating bonds, they're pretty large molecules, and they have many degrees of freedom. So docking runs for them are not going to take seconds, they're going to take hours. And we know the force field-based scoring functions are of mediocre accuracy, R squared of about 0.5 to real life. This is not algo trading. If you could do that in the stock market, you'd be very rich, but in chemistry it's not so great. So high cost, low accuracy make this unattractive. So what's reinforcement learning? Essentially what we're doing is we have agents or bots, and what these bots do is they use quick heuristics to select a sequence and conformation and dock the peptide. So the sequence, the conformational search is not done specifically for the individual peptide, but we have a database of conformational searches, and the database is obviously linked with one member to another, so you can go from here to here without having to explicitly simulate that on the protein structure, and then dock it in there. And then the bot gets a reward for how good the docking was done. So in our case, it's obviously going to be the docking score, but it's going to be discounted for innovation. And I'll explain why in a second. So the bots talk and share information with one another. They learn from one another and improve as they go along. So how can we make it go faster and better? So for example, if one bot successfully docked the Amit sequence, which happens to be my name, so it's alanine, methionine, isoleucine, and threonine. Another bot now wants to dock the alanine, norleucine, isoleucine, and threonine sequence, where we know that methionine and norleucine are very similar. So this bot can now exploit the dock structure of Amit. So it can go in and basically just thread this peptide on the existing peptide. It will give it a very quick reward for time, right? Very quick, but not very innovative. So this is an exploit possibility. It's a very simple case. Whereas it could also decide to explore and do a whole new docking experiment without the threading. And basically, we reward innovation more. But you have to know, the bot has to learn when it can thread and do a quick takeaway from another dock position, and when it needs to go and explore. And then obviously this is not a binary function of explore, exploit. You can do explore and exploit in several different parts of the decision tree, and get rewarded if you do everything very explorative, but also if you do a good exploit. So what we have is the very balanced solution set, where we're kind of trying to eliminate idiosyncratic risk, and I'll explain that in a second. And this is all based on the Nobel Prize-winning economist Professor Harry Markowitz and his modern portfolio theory, the MPT, and we started this thinking in Neil's lab over 10 years ago. So think about, I always like to use a simple analogy to explain. So suppose we want to teach a machine how to play basketball, because we talk too much about molecules, right? So one way to do is to take all the old films of the NBA and to have a big data approach, and then have the software look into what plays are done in the NBA and learn how to mimic them, right? So this would be big data learning. Another way would be to simulate the basketball game physically, right? Now, if we could simulate everything physically perfectly, we would not be doing big data discovery, right? If we had if the docking score would be exactly what you'd get when you test it in the lab, none of us would be doing big data. We'd all be docking stuff all the time. But we know that it's not that good. So, in theory, this is perfect. In reality, hard to do, not perfect. So, suppose I simulated a basketball game, 5 minutes, and I forgot about hand vibrations, right? So now we've got these bots playing basketball. They're throwing 3-pointers. In fact, they're not dribbling, they're not passing the ball. They're getting the ball immediately, shooting, getting their 3 points. We have a game of 3 points being played. This is not basketball. But we decided it's 3 points because it's hard for humans to do that. But we have a supply and demand curve. Now we see that everybody's throwing 3 points. 3 points become 2 points, 1 point, half a point, etc. It decays, right? And then all of a sudden, passing the ball, dribbling, passing to another guy, and dunking it is worth 3 points. So eventually what we're doing is we're kind of diversifying the lack of knowledge we have in the basketball game, and eventually we're reaching something that has a completely different point system, but does look like a basketball game. I hope that was kind of clear. That's as fast as I can go explaining what we're doing. I'll give some examples of how this works. So we're working on psoriasis, just to see some of the chemical space. This is an active molecule, but not one we're continuing on. We can see we have cyclohexylamine, we've got NALs, we've got a macrocycle, and we have a lasso. So basically we have an isoasp, and then we're breaking out with more peptide sequence out of that. We can see we have DAP here, completely non-natural molecule. And then we're looking at human serum proteolytic stability. These are control peptides that are actually very active on the target, but these are our peptides, T1/2 over 200 minutes, close to 300. So this is an example of, this is a year old, so now we're more potent than this. So we've taken a peptide that came out of the game. We used improvement bonds, just kind of threading different lassos and sequences on it. Went from single-digit micromolar to 150 nanomolar, and then towards the mouth. So these are already more potent than that. But this is from our first experiment. We already passed the fourth. We're taking mice in a model that gives them psoriasis, so we can see the control epidermis here, the untreated, sick, psoriatic one here. This is the one treated, and this is the area that we're kind of measuring treated with a steroid drug that's currently in use today, and with family 17 and family 10. Basically, you can see a great reduction in the psoriatic lesion size. This is a potent natural peptide called HAP. Very potent nanomolar, not natural in that it comes from the body, natural as far as the sequence came from a drug company. You can see that the non-natural macrocycles perform better than HAP. We can also see it when we look at the biochemistry of it. We can see that our peptides were able to reduce TNF alpha, in this case better than HAP, similar than HAP. In this case, interferon gamma, both better than HAP. This is the clinically used drug that doesn't do anything on TNF alpha. That's why we need to go out of steroid drugs. And we can see a nice effect here, good half-life, serum proteolytic stability, etc. Just another little note. So this is a project we're doing with one of the large companies in the world, large pharma and agricultural companies in the world. In this case, we're screening for a certain target that I can't talk about. But in the first screening run, we had several peptides at the single-digit nanomolar range, 4, 3.8, 8.8, and some of higher affinities in IC50s. So we can see that this really makes things quicker and cheaper. I just want to thank our scientific advisory team today, headed by Tommy Sawyer. We also have Walid Ganho on board and Richard Saul, all great chemists, peptides. And our team, which I'm not going to go through because we don't have time. Any questions?
Thank you, Amit, for this presentation, and I'm opening for questions, if any.
When you use this peptide in vivo, how will you guarantee that this peptide will not attack by the immune system, that the body will develop antibody against it?
We can't guarantee that. What we're doing is trying to, and I think the word that Hanoch used was diversify, and that's a critical issue. So the two peptides I showed you that came out of the computer are not similar. They're not from the same family. One of them is a direct inhibitor, another one is an allosteric inhibitor. They bind to completely different sites They have no correlation in their chemical composition. And basically, the chances that I'm going to get an adverse immune response, they exist. But my chances of in two non-correlated molecules, molecular families, each have dozens of active variants, of failing in all of them are tiny. So it's like throwing dice. Your chance of getting 6 is 1/6, but your chance of getting 6 sixes is 1/6 to the power 6. If you diversify, if you throw the same dice with the same angle and same figure, it's not diversification because you have an autocorrelation issue. The sequence, the size, the conformations have different descriptors, so they go within different descriptors. So what descriptor would you like? It's like saying, what restaurant do you go to in Tel Aviv here? What do you like to eat there? And then which restaurant, which street, but again, I give you all the information, you decide which one to take, where if you completely copy me, you're going to get a very reduced score for being too much of a copycat. I never even really counted it, so it's a whole bunch. It's a place on the grid to start, the kind of sequence to connect to that place on the grid, etc., etc. There's several grids. Which grid to use? Yeah, starting with me and then my team. It's a growing list, and a lot of it may be redundant. We're just now starting to see if there's two things that really, they're kind of the same thing. Yeah, it's fun. So I love to play video games and I love to look for drugs. So I'm playing a video game that looks for drugs. No, I'm not good at that.